What if the human mind could be translated into perfect symbols? Before computers, before modern logic, one man dared to dream of it. His name was Giuseppe Peano, the genius who wanted to transform thought into mathematics. The greatest mathematicians of all time. Episode 21. Giuseppe Peano.
Giuseppe Peano was born on August 27, 1858, in Cuneo, Piedmont, Kingdom of Sardinia, present-day Italy, and died on April 20, 1932, in Turin, Italy. Giuseppe Peano's parents worked on a farm, and Giuseppe was born in the country house Tetto Gallant, about 5 kilometers from Cuneo. He attended the village school in Spinetta and later moved to the school in Cuneo, making the 5-kilometer round trip on foot every day. His parents bought a house in Cuneo, but his father continued to work in the fields of Tetto Gallant with the help of Giuseppe's brother and sister, while his mother remained in Cuneo with Giuseppe and his older brother. Giuseppe's mother had a brother who was a priest and lawyer in Turin, and, realizing that Giuseppe was a very talented child, took him to Turin in 1970 so that he could attend secondary school and prepare for university studies. Giuseppe took the exams at the Ginnasio Cavour in 1873, and then attended the Liceo Cavour, where he graduated in 1876, and in that same year entered the University of Turin. Among Peano's teachers in his first year at the University of Turin was Dovidio, who taught him analytical geometry and algebra. In his second year, he took calculus classes with Angelo Ginocchi and descriptive geometry with Giuseppe Bruno. Peano continued to study pure mathematics in his third year and discovered that he was the only student to do so. The others had continued their studies at the School of Engineering, which Peano himself originally intended to attend. In his third year, Francesco Fa di Bruno taught him analysis and Dovidio geometry. Among his teachers in his final year were again Dovidio with a new course in geometry and Francesco Ciacchi with a course of mechanics. On September 29, 1880, Peano graduated with a doctorate in mathematics. Peano joined the faculty of the University of Turin in 1880, being appointed assistant to Dovidio. He published his first mathematical paper in 1880 and 3 more papers the following year. Peano was appointed assistant to Ginocchi between 1881 and 1882. And it was in 1882 that Peano made a discovery that would be typical of his style for many years, an error in a standard definition.
Ginocchi was already quite old and in relatively poor health, and Peano inherited some of his classes. Peano was about to teach the students about the area of a curved surface when he realized that the definition in Surrect, which was the standard text for the course, was incorrect. Peano immediately told Ginocchi about his discovery, to which Ginocchi replied that he already knew. Ginocchi had been informed the previous year by Schwartz, who appears to have been the first to find Surrett's error.
In 1884, a text based on Ginocchi's lectures in Turin was published. This book, Course in Infinitesimal Calculus, although based on Ginocchi's lectures, was edited by Peano, and in fact contains much material written by Peano himself. The book itself states on the title page that it is published with additions by Dr. Giuseppe Peano. Giannacci seemed somewhat displeased that the work had been published under his name, as he wrote, "The volume contains important additions, some modifications, and several annotations which are presented first. So that nothing may be attributed to me that is not mine, I must declare that I did not participate in the compilation of the aforementioned book, and that everything is due to the remarkable young Dr. Giuseppe Peano." Peano obtained his qualification to be a university professor in December 1884 and continued to teach, including to Giannacci, whose health had not yet recovered sufficiently to allow his return to the university. In 1886, Peano proved that if the function f of x is continuous, then the first-order differential equation expressing the derivative of y with respect to x equal to f of x has a solution. The existence of solutions with stronger hypotheses about the function f had already been demonstrated previously by Cauchy and later by Lipschitz. 4 years later, Peano showed that the solutions were not necessarily unique, giving as an example the differential equation in which the derivative of y with respect to x is equal to 3 times y raised to the 2/3 power, with the initial condition that y at the point x equal to 0 is equal to 0. In addition to teaching at the University of Turin, Peano began teaching at the Turin Military Academy in 1886. The following year, he discovered and published a method for solving systems of linear differential equations using successive approximations. However, Émile Picard had already discovered this method independently and attributed the initial discovery to Schwarz. In 1888, Peano published the book Geometric Calculus, which begins with a chapter on mathematical logic. This was his first work on the subject that would play a fundamental role in his research in the following years, and it was based on the works of Schroeder, Boole, and Charles Peirce. An even more significant feature of the book is that in it, Peano sets forth with great clarity the ideas of Grossman, which were certainly presented in a somewhat obscure way by Grossman himself. This book contains the first definition of a vector space, presented with a remarkably modern notation and style, and although it was not appreciated by many at the time, it is certainly a remarkable achievement of Peano.
In 1889, Peano published his famous axioms, known as Peano's axioms, which defined natural numbers in terms of sets. These were published in a pamphlet entitled Arithmeticius, Principles of Arithmetic and the New Method Explained, which, according to H.C. Kennedy in Peano, Life and Work of Giuseppe Peano, were a landmark both in the history of mathematical logic and in the foundations of mathematics. The pamphlet was written in Latin, and no one could give a good reason for this except for H.C. Kennedy. It seems to be an act of pure romanticism, perhaps the only romantic act in his scientific career. Giannacci died in 1889, and Peano hoped to be appointed to his chair. He wrote to Casorati, whom he believed to be part of the nomination committee, requesting information, only to discover that there was a delay due to the difficulty in finding enough members to compose the committee. Casorati had been contacted, but his health did not permit the task. Before the appointment could be made, Peano published another impressive result. He invented space-filling curves in 1890. These are continuous and surjective maps from 0, 1 to the unit square. Hilbert, in 1891, described similar space-filling curves. It was believed that such curves could not exist. Cantor had demonstrated that there is a bijection between the interval 0, 1 and the unit square, but shortly afterwards, Johannes Netto proved that such a bijection cannot be continuous.
Peano's continuous space-filling curves cannot be injective, of course. Otherwise, Netto's theorem would be contradicted. Hausdorff wrote about Peano's result in Foundations of Set Theory in 1914.
This is one of the most remarkable facts of set theory. In December 1890, Peano's wait to be appointed to the Giannocchi chair ended when, after the usual competition, the position was offered to him. In 1891, Peano founded the Rivista di Matematica, a journal dedicated primarily to logic and the foundations of mathematics. The first article in the first part is a 10-page text by Peano, summarizing his work in mathematical logic up to that point. Peano had great skill in perceiving which theorems were incorrect, identifying exceptions. Others were not so satisfied with the pointing out of these errors, and one of them was his colleague Corrado Segre. When Corrado Segre submitted an article to Rivista di Matematica, Peano pointed out that some of the theorems contained exceptions. Segre was not willing to simply correct the theorems by adding conditions that excluded the exceptions, but defended his work by saying that the moment of discovery was more important than a rigorous formulation. Of course, this went very much against Peano's rigorous approach to mathematics, and he argued vehemently, "I believe it is something unprecedented in the history of mathematics that authors consciously use in their research propositions for which exceptions are known or for which they have no proofs." It was not only Corrado Segre who suffered from Peano's exceptional ability to detect a lack of rigor. Of course, it was the precision of his reasoning, combined with the accuracy of his mathematical logic, that gave Peano this clarity of thought. Peano pointed out an error in a demonstration by Hermann Laurent in 1892, and in the same year reviewed a book by Veronese, concluding the review with the following comment: "We could continue enumerating at length the absurdities that the author has accumulated. But these errors, the lack of precision and rigor throughout the book, detract from its value." Around 1892, Peano embarked on a new and extremely ambitious project, the Formulario Matematico. He explained his reasoning in the March 1892 edition of the Rivista di Matematica.
Of great use would be the publication of collections of all currently known theorems relating to certain branches of mathematical sciences. Such a collection, which would be long and complex in common language, becomes considerably easier with the use of mathematical logic notation. In many ways, this great idea marks the end of Peano's extraordinary creative work. It was a project received with enthusiasm by some, and with little interest by most. Peano began trying to convince everyone around him of the importance of this project, which ended up irritating them. However, Peano and his closest collaborators, including his assistants, Vailotti, Burali-Forti, Pieri, and Fano, soon became deeply involved with the work. In describing a new edition of the Formulario Mathematico in 1896, Peano wrote, "Each professor may adopt this formulario as a textbook, as it should contain all the theorems and all the methods. His teaching will consist of showing how to read the formulas and pointing out to the students the theorems he wants to explain in his course." When the Formulario Calculus volume was published, Peano, as he had indicated, began using it in his classes. This was the disaster that could be expected. Peano, who was a good teacher at the beginning of his academic career, became unacceptable to both his students and his colleagues because of his teaching style. One of his students, who was actually a great admirer of Peano, wrote, "But we students knew that this instruction was beyond our comprehension. We understood that such a subtle analysis of concepts, such a meticulous critique of the definitions used by other authors was not suitable for beginners, and especially not useful for engineering students. We didn't like having to devote time and effort to symbols that we might never use years later. The military academy terminated his teaching contract in 1901, and although many of his colleagues at the university also wished him to stop teaching there, nothing was possible due to the institution's structure. The professor was an unquestionable authority in his field, and Peano was unwilling to listen to his colleagues when they tried to convince him to return to his old teaching style. The Formulario Mathematico project was completed in 1908, and Peano's achievements are admirable, but although the work contained a wealth of information, it was little used.
However, perhaps Peano's greatest triumph occurred in 1900. That year, 2 congresses were held in Paris. The first was the International Congress of Philosophy, which began in Paris on August 1st. It was a triumph for Peano, and Russell, who participated in the Congress, wrote in his autobiography, "The Congress was a turning point in my intellectual life, for there I met Peano. I already knew him by name and had seen some of his work, but I hadn't bothered to master his notation. In the discussions at the Congress, I observed that he was always more precise than anyone else, and that he invariably prevailed in any argument he initiated. As the days went by, I concluded that this was due to his mathematical logic. It became clear to me that his notation offered an instrument of logical analysis such as the one I had been seeking for years." The day after the end of the Congress of Philosophy, the Second International Congress of Mathematicians began. Peano remained in Paris for this Congress and attended Hilbert's lecture, in which he presented 10 of the 23 problems contained in his paper, whose objective was to define the agenda for the following century. Peano was particularly interested in the second problem, which questioned whether the axioms of arithmetic could be proven consistent. Even before completing the Formulario Mathematico project, Peano was already beginning the next great project of his life. In 1903, Peano expressed interest in finding a universal or international language, and proposed an artificial language, Latino sine flexione, based on Latin but devoid of any grammar. He compiled the vocabulary using words from English, French, German, and Latin. In fact, the final edition of the Formulario Mathematico was written in Latino sine flexione, which is another reason why the work was so little used.
Peano's career, therefore, was divided in a rather peculiar way into 2 periods. The period up to 1900 was marked by great originality and a remarkable sensitivity to themes that would be important for the development of mathematics. His achievements were extraordinary, and he possessed a modern style, quite inappropriate for his time. However, this sensitivity to what was important seemed to abandon him, and after 1900, he worked with great enthusiasm on 2 very difficult projects, which were enormous undertakings, but which proved to be of little relevance to the development of mathematics. Regarding his personality, Kennedy writes, "I am fascinated by his gentle personality, his ability to attract lifelong disciples, his tolerance of human weakness, and his perennial optimism. Peano can not only be classified as a mathematician and logician of the 19th century, but, due to his originality and influence, he must be considered one of the great scientists of that century. Although Peano is one of the founders of mathematical logic, the German mathematical philosopher Gottlob Frege is today considered the father of mathematical logic. Peano taught at the University of Turin until his death from a heart attack in 1932, one day after his last lecture.
Giuseppe Peano departed, leaving behind a code, an echo of pure reasoning that still resonates in the mind of every scientist and programmer in the modern world. His life was brief, but his dream was eternal: to transform human reason into a universal language.